Bismillahirrahmanirrahim. Hello students, welcome to another video. This is Hamza Noor from Aero Education Network, and today I'm going to discuss some past paper questions for Cambridge Mechanics A-Level Maths 9709, and the topic is specifically forces and equilibrium, particularly dealing with the subtopic contact forces. And here we have some past paper questions from the handout of contact forces. First of all, we have handout question number 5, which is May-June 2009, paper 4, question number 4. So these are basically the classwork notes. So I'm just making a lecture in English as a walkthrough of all the solutions of the classwork notes. Okay, so the questions are already solved in the class, but I want to make some lectures in English for my YouTube channel. So it's like a walkthrough video. Okay. So the question is saying that a block of mass 8 kg is at rest on a plane inclined at an angle of 20 degree to the horizontal. The block is connected to a vertical wall at the top of the plane by a string. The string is taut and parallel to a line of greatest slope of the plane, as you can see in the diagram. So the requirement of part 1 is to, given that the tension, here we have a condition that given that the tension in the string is 13 Newton, find the frictional and the normal components of the force exerted on the block by the plane. So, first of all, we are going to uh, mention all the forces which are acting on the block. Okay, so since we know that the plane is inclined at an angle of 20 degree to the horizontal, and the weight of the block will be 8 Newton. Weight always acts vertically downwards. Okay, since the mass is 8 kg, so the weight is 8 Newton. All right, and since the angle over here is 20 degrees, so this angle would also be 20 degrees. Okay, we are going to resolve the component of the weight, okay, in this way that they are perpendicular to the plane or they are parallel to the plane. Okay, so the component which is perpendicular with the plane is 8g cos 20 because this component is adjacent with this angle, and along the plane the component is 8g sine 20 because this is opposite to this angle. And as you know that the normal contact force always acts perpendicular with the surface, so here it is acting upwards, okay, since the block is in contact with the surface. And the block is basically connected by a string, and the tension in the string has a magnitude of 13 Newton. So this basically force is a pulling force. Okay, so when I'm referring to this block, so the tension in the string is moving away from this block, okay, with a magnitude of 13 Newton. All right. And as we know that, this block is in equilibrium, okay, the block is in equilibrium, block is held in the state of rest. Okay, block is held in the state of rest. So the forces which are acting up the plane and the forces which are acting down the plane, they should be balanced. They should be equal. And here you just calculate the value of 8g sine 20. Meaning you just put this in your calculator, 8 into 10 into sine 20. So you would be able to see that the magnitude of 8g sine 20 is greater than the magnitude of 13. Okay, this means that, the frictional force would act upwards in order to make the force balanced because, the block is in the state of rest. Okay, so this is basically the thing. All right, so 8g sine 20 has a higher magnitude as compared to 13. So therefore, the friction will act upwards. So here I have mentioned that the friction will act up the plane. Okay, so therefore we are going to say that this 13 Newton and the frictional force will act in the same path. So 13 plus F minus 8g sine 20 is equal to 0 because you know that forces will have a sum of 0 since the block is in rest equilibrium. Okay, so it is stationary. All right. So F is equals to 8g sine 20 minus 13, where g is equals to 10. So we just calculate this thing and correct to three significant figures. The frictional force has a magnitude of 14.4 Newton. Okay. And then we are going to find the value of R, meaning we are going to find the normal contact force. Okay, so we are going to resolve the forces perpendicular with the plane. So R minus 8g cos 20 will be equal to 0. So this means R is equal to 8 into 10 into cos 20. Therefore, magnitude is the magnitude of R is 75.2 Newton. Here was the requirement of part 1. It was required to find the frictional and the normal components of the force exerted by the block on the plane. Now, in part 2, we have another situation that the string is cut. This string is basically cut now. Okay, so the magnitude of the tension in the string will become 0, obviously. The block remains at rest, but it is on the point of slipping down the plane. Okay, this means that the block is not actually moving, it is just about to move. It is on the point of slipping down the plane. So this particular situation is known as limiting equilibrium. Okay, when the object is on the point of slipping, on the point of moving, it is not actually moving, it is just about to move. Okay, so this situation is known as limiting equilibrium. Okay, so in this particular situation, the friction is on the maximum value. Friction is F lim, F max. I hope you have covered all of the basic concepts in detail before actually solving the past paper questions. Okay, so the frictional force will be maximum. Friction would be maximum when the object is on the point of moving, meaning when the object is about to move, and when the object is actually moving, also in that particular case, it would be the same, that the frictional force will be at its maximum value, F lim, F max. Okay, so I hope you have covered all of the basic concepts in detail. All right. So basically, when the string is cut, so the tension in the string becomes 0. So T is equal to 0. Okay, so obviously, the force which is acting over here along the plane 8g sine 20, and upwards we have the frictional force, obviously. Okay, because the plane is rough, as you already know this, and this friction would have a maximum value now. Okay, this friction would have a maximum value F lim, or you can just say F max, which is equals to mu R. All right. So F lim is equals to mu R. This would be the maximum friction. So F minus 8g sine 20 is equal to 0. F is equals to 8 into 10 into sine 20. So F is equals to 80 sine 20. This means that the maximum friction F lim F max is basically 80 sine 20. And as we know the fact that the magnitude of the normal contact force is found by this expression 80 cos 20. I want to find an accurate value correct to 3SF for the coefficient of friction. So I'm going to use this exact expression over here. So therefore 80 sine 20 is equals to mu multiplied by 80 cos 20. Therefore the coefficient of friction is 80 sine 20 divided by 80 cos 20. So 80 got cancelled out, and sine 20 divided by cos 20, you can write the identity which you are studying since P1. Okay, so mu is equals to 0.364, correct to three significant figures is your answer. Okay, this friction would have a maximum value in this situation. Okay, so 80 sine 20 is basically the maximum friction which we are looking for. This will be equals to mu R. Either you can say F lim, or you can say F max. All right. So this was basically handout question number 5, which is May June 2009 paper 4, question number 4. So now let's move on to the next question. Up next we have handout question number 6, which is October November 2009 paper 4 variant 2, question number 1. So the question says that a small block of weight 12 Newton is at rest on a smooth plane inclined at an angle of 40 degree to the horizontal. The block is held in equilibrium by a force of magnitude P Newton. Find the value of P when the force is parallel to the plane as shown in figure 1. Okay, and then in part 2 we have another figure in which this force P is horizontal. Okay, so let's just focus on part 1. Okay, so basically the force P is acting up the plane, along the plane in this way. All right, so first of all, the weight of the particle. Okay, the weight component is already given to you. Okay, so weight component is already given to you. So the component of the weight which is adjacent to this angle would be, this would be the force, which is 12 cos 40, because this is adjacent to the angle of 40. When this angle is 40, so obviously this angle is also 40. Okay, we have covered this in detail in the basic concepts, all right, when we were dealing with inclined planes. So this is basically the component of the weight which is perpendicular with the plane, and here we have the component which is along the plane, which is basically opposite to the angle 40. Okay, and then here we have the normal contact force which is perpendicular with the plane always. Okay, and P is acting up the plane. So basically the block is at rest and the plane is smooth. So when plane is smooth, so there is no friction. So therefore we are going to say that P minus 12 sine 40 is equal to 0. Therefore P is equal to 12 sine 40 and P is equal to 7.71 Newton, correct to 3SF. So this was the complete working of part 1, which was worth 2 marks. Then we have part 2, which says that when the force is horizontal. Okay, so P force is now horizontal. All right, so the weight of the block is going to act in the same way. Okay, and here we have the component which is adjacent with the angle 40, meaning perpendicular with the plane, and this component is along the plane. I'm just going to make it more accurately over here. All right, so so here is the component of the weight which is along the plane. Now the thing is that this P Newton force is acting horizontal. Okay, so according to the alternate angles property, when this angle is 40 degree, okay, so this angle is also 40 degree, which means this angle is also 40 degree. Okay, you can just consider this thing. All right, so if this angle is 40, so obviously this angle is 40 according to the corresponding angles, and according to alternate angles, this angle is 40 degree. Okay, so this is basically the whole idea. So basically this P Newton force will have a component which is perpendicular with the plane. Okay, this is opposite to this angle 40, so this is P sine 40. All right, and P cos 40 would be acting upwards along the plane which is adjacent to the angle of 40 degrees. Okay, what we are doing, we are basically resolving the forces perpendicular with the plane and parallel to the plane. Okay, and since the plane is smooth, so there is no friction at all. All right, so and since the block is in equilibrium in both of the cases, okay, so P cos 40 minus 12 sine 40 will be equal to 0. All right, so P will be equal to 12 sine 40 divided by cos 40. Here I've again used the identity. It's not compulsory to use the identity, okay, unless there is a specific form which you need to show in your answer. Okay, but in this case, you can just put this expression in your calculator, that P is equal to 12 sine 40 divided by cos 40. So P is equal to 10.1 Newton, correct to 3 significant figures is your answer. Okay. I hope my voice is not glitching because today the internet connection is unstable a little bit. So let's see. So this was basically the question number 6 of the handout. After this, we have handout question number 7, which is October 2009, paper 42, question number 5, same paper. So the question is saying that a small ring having the same weight, which is 12 Newton, is threaded on a fixed rough horizontal rod. And then it says that a light string is attached to the ring and the string is pulled with a force of 15 Newton at an angle of 30 degrees to the horizontal. In part 1, it says that when the angle of 30 degrees is below the horizontal, okay, so the ring is in limiting equilibrium, okay. This means that the ring is on the point of sliding, about to move. It's not actually moving, it's about to move, okay. Show that the coefficient of friction between the ring and the rod is 0.666, correct to three significant figures. All right, so first thing first, we are just going to focus on this sketch where 15 Newton is acting at an angle of 30 degrees below the horizontal, okay. So 15 cos 30 will be towards left, okay, since this is adjacent to the angle 30, okay, and 15 sine 30 will be acting towards down because this is opposite to the angle 30, okay. And here we have the weight, and opposite to this weight is basically the normal contact force, which acts according to the Newton's third law of motion, as you have studied in the basic concepts. All right. And since this 15 cos 30 is trying to pull this ring towards the left, it's not actually moving, but we can say that the ring is about to slip towards left because 15 cos 30 is acting towards left. So the friction would be acting on the opposite path. As you are aware that the friction is against the tendency of moving. Okay. So, and the friction would be at its maximum value, F lim or F max, or you can just simply say mu r. Okay. F lim is equals to mu r, or you can say F max is equals to mu r. So either you can mention mu r over here, or you can mention F max or F lim as well. Both are fine. So what is happening that the ring is on the point of slipping. Okay, so the sum of the forces will be equal to 0. So 15 cos 30 minus mu r is equal to 0. Okay, because 15 cos 30 is towards left and mu r is towards the right. So 15 cos 30 minus mu r is equal to 0. And here I've done the working for finding r. Okay, so r is acting upwards. In the opposite path you have the weight of the ring, and 15 sine 30 is also acting in the opposite path of r. So r minus 12 minus 15 sine 30 is equal to 0. So here we have an exact expression for r. Okay, and here I've mentioned this expression over here. So 15 cos 30 is equals to mu r, and therefore the coefficient of friction mu is equals to 15 cos 30 divided by 12 plus 15 sine 30. Okay, so first I've mentioned the exact value, which is 5 root 3 divided by 13, and mu is equals to 0.666. All right, so this is how you attempt this. We have shown 0.666 correct to three significant figures. Then we have part 2. Part 2, when the angle of 30 degree is above the horizontal, as you can see in this figure 2, the ring is moving with acceleration a meter per second square. Find the value of a. Okay. So now basically, this 15, the force which is having a magnitude of 15, it is acting up, inclined at an angle of 30 degree to the horizontal, and it is acting, you know, above the horizontal. So, obviously this would make sense that the R would change, isn't it? Because now this 15 force would have a component which is acting up the rod. It would be 15 sine 30. This makes sense or not? But the coefficient of friction will not change. It will remain same. It remains same. Okay. So basically what's going to change is the magnitude of the normal contact force. So basically mu is just the ratio of the frictional force with the normal contact force. Okay. So this is basically the whole scenario, mu will remain same, the coefficient of friction will remain same. Either you can use this 0.666 as well, or you can use this exact value as well in order to avoid, premature approximations. In this case, 0.666 would also be fine. So it's actually recommended that you use the exact value in your further calculations, or you can use a value which is basically to a higher state of accuracy in order to avoid premature approximations. All right, so that is basically the whole idea. What I'm trying to say is that R is going to change in this case because 15 sine 30 force is now acting up the rod. Okay, so I'm going to say that R plus 15 sine 30 minus 12 is equal to 0. So R is equals to 4.5 Newton. Okay, this is basically an exact value of R. All right, and then I'm going to say that 15 cos 30 minus mu R will be equals to mass times acceleration, because 15 cos 30 is pulling this ring towards left, and now the ring is accelerating, and mu R is in the opposite path because this friction would have a maximum value again. Okay, when the object is on the point of moving and when it is moving, in both of these cases, friction would be at its maximum value, as we have covered in the basic concepts before attempting the past paper questions, before actually starting the past paper questions. So 15 cos 30 minus mu r is equal to mass times acceleration. This equation is established by the Newton's second law of motion. Okay, so 15 cos 30 minus, in place of mu, I'm going to write 5 root 3 divided by 13. And in place of r, I'm going to write 4.5. This will be equals to 1.2a. Okay, and therefore, first I have done some working in an exact form. Acceleration is equal to 75 root 3 over 13 divided by 1.2, because we need to find the mass as well, right? Here I've done the working for mass. Okay, since weight is equals to mg, and in Cambridge mechanics we take g is equals to 10. Okay, strictly speaking, and the weight is given to us in the question. So mass is basically 1.2 kg. Okay, so you need to be careful when the mass is given to you and when the weight is given to you. Okay, in this question, the weight was given to you, but mass you need to find like this. All right, so mass is basically 1.2 kg, and therefore the value of acceleration is 8.33 meter per second square, correct to three significant figures. All right, so this was basically handout question number 7, October November 2009, paper 4, variant 2, question number 5. All right, so for the sake of this video, I've discussed these three questions over here. Okay, in my next video I'm going to discuss two more questions, and then inshallah I'll be making more videos like this. I believe this was a like more efficient and effective way, you know, to just discuss the walkthrough lectures by showing the classwork notes, okay, which I have basically discussed with my students, okay, in the class. And I want to make some more videos. I want to make more and more content in English, particularly for my YouTube channel. Okay, so that's the reason. All right. Instead of, making the whole lecture from scratch. So in this recording, I have discussed these three questions. So stay tuned to my channel. Thanks for watching. Assalamu alaikum.